Alright guys, welcome to this page of the notes. Here's what we're going to do. We're going to keep going with this theme of proving parallel lines using our converse statements. So here's what I want you to do. I want you to prove that line L and line, or L1 and L2, L1 and L2 are parallel, right? Using the values that I've given you. Hopefully you can see there. If not, I will put them in for you. I have tile right here in red. This one is yellow. This one is blue. And this one is green. What I've done is I have given you, right, the measure 1 and 2. Using those angles, the measure of angle 1 and the measure of angle 2, can you prove L1 and L2 are parallel lines? Okay, let's see what we can do. If you guys remember that tile that I drew for you on the previous page, right? Here's what we said. We said that these bottom angles down here were 60 degrees, right? And these angles up here in the top were what? Were they 120? I think they were 120, right? Yeah, 120 degrees. So 120, this guy right here. Was 120 degrees. All right, so here's what I know. That means then that angle 1, that guy right there, has to be 120 degrees. So I know the measure of angle 1 is 120 degrees. I know that the measure of angle 2 must also then be 120 degrees. Okay, here's what we're going to do. I'm going to use that converse statement that's this one. It is the converse of the corresponding angles theorem. So converse of corresponding angles theorem. Let's go back and take a look at what it said. Here's what it says. That converse of the corresponding angles theorem says this. Converse corresponding angles theorem. If I can prove, if I can show that any pair of corresponding angles, are congruent. If I can show you corresponding angles are congruent, then the lines must be parallel. Well, here you go. Right? Angle 1 is in the top left-hand corner of that intersection, top left-hand corner. Angle 2 is in the top left-hand corner of a different intersection. That is our definition of corresponding angles. They're in the same position of different intersections. So here's what I know. I know that the measure of angle 1 is congruent to the measure of angle 2 because they're corresponding angles. Right? They're corresponding angles. Well, here's what I've just done. I have just proven, right? Corresponding angles, that means that they're congruent. They're both equal to 120 degrees. If I can show you corresponding angles are congruent, and I just did, 120 degrees equals 120 degrees, right? That 120 equals 120, right? So I've shown you, right, corresponding angles are congruent. If I can show you that corresponding angles are congruent, then the lines must be parallel. The lines must be parallel. So angle 1 is congruent to angle 2. They're corresponding angles. So that means then that L1 is parallel to L2. And how did I do that? I used this theorem right here, converse of corresponding angles theorem. The converse of the corresponding angles theorem. Okay, let's do another one. All right, here's what I've done. I've given you a diagram, this guy right here, diagram, and the following angle relationships. I want you to prove that line L is parallel to line M. Can we prove line L is parallel to line M. Okay, here's what I tell you. The first one, I tell you that angle 3 and angle 5 are congruent. So based on that, in my diagram, I know that angle 3 and angle 5 are congruent. Now, can I use that information, angle 3 and angle 5, knowing that they are congruent? Can I prove L and M are parallel lines? Well, I can. Right here, if you guys go back to the converse of alternate interior angles theorem. Let's go back and look at it. It's right here. Alternate interior angles theorem, right there. Converse, alternate interior angle theorem. If I can prove, right, any pair of alternate interior angles are congruent. If I can prove that they're congruent, then the lines are parallel. Well, look what I told you. 3 and 5 are congruent. 3 and 5 are alternate interior angles. If alternate interior angles are congruent, then the lines must be parallel. Therefore, L is parallel to M. How do I know that? Well, I know that based on this theorem, the converse of the alternate interior angles theorem. Let's do another one. Same diagram, this diagram right here, but now what we're going to do, measure of angle 4 is equal to this. The measure of angle 8 is equal to this, and x is 15. I want you to prove L and M are parallel lines. Well, let's take a look at this. Angle 4, right there. Angle 8, right there. What do we know about angle 4 and angle 8? Well, if I can prove angle 4 and angle 8 are congruent, please notice they're corresponding angles. Angle 4 is in the bottom left-hand corner. Angle 8 is in the bottom left-hand corner. They're corresponding angles. If I can prove that those corresponding angles are equal, then I've proven these lines must be parallel. So let's see if we can do that. Can I show that? Well, here we go. The measure of angle 4 is equal to x plus 20. So the measure of angle 4 is equal to, please notice, x is 15. So the measure of angle 4 is equal to 35. Here we go. Measure of angle 8 is equal to 2x plus 5. Keep going. Measure of angle 8. I know what x is. It's 15. Plug it in. 2 times 15 plus 5. Measure of angle 8. Guys, plug and chug. Don't fat finger something on your calculator, but I think you can probably do this in your head. 2 times 15 is 30. 30 plus 5 is 35. Here's what I've just done. I have just proven the measure of angle 4 is congruent to the measure of angle 8. There, right? 35, 35. I've just proven angle 4 and angle 8 are congruent. And since they're corresponding angles, I can use the converse of corresponding angles theorem to prove that my lines are parallel. So I'm going to use the converse of corresponding converse of the corresponding angles theorem what that does, right? If I can prove corresponding angles are congruent, then the theorem says the lines must be parallel. Well, I just showed you. Corresponding angles are congruent. We just proved it. So what does that mean? Well, that means that L is parallel to M, which is exactly what I was trying to show. All right, I got one last thing for you guys here in this section. So if you head on over to the next page, I've just got this one last postulate for you guys, and here it is. It's really a pretty simple postulate. This postulate guarantees that for any line L, you can always construct a parallel line through any point that is not on L. I know it sounds really wordy. I promise you it's a really simple idea. Let me show you. Let's call this guy right, oh, that's my highlighter. Don't want that. This guy right here. Let's call that guy right there line L. Now what I need, if that's line L, I need a point that is not on line L. You can draw your point anywhere you want to as long as the point isn't on line L. Let me go ahead and put my point, I don't know, right there. That looks like a good spot to put a point. I'll put a point right there. Now here's what this postulate says. This postulate says, or guarantees, it guarantees that for any line L, here's my line L, I can draw or construct a parallel line through this point, right? That's parallel to line L. Now there's an infinite number of ways to draw a line through that point. I could draw a line through that point like this. Right, there's a line. There's a line and it's going through that point. But are these lines parallel? No. I could draw a line that goes through that point that looks like this. Right? There's a line. It goes through the point. But is that line parallel to line L? No. What I'm saying, what this postulate is saying is it is guaranteeing, right, that yes, there's an infinite number of ways, to draw a line through that point. But it is guaranteeing that at least one of those infinite possibilities, is going to be parallel. And here it is right here. Well, I'm freehanding this, so as best as I can do, hopefully those guys look parallel to you. I think that's pretty good for freehanding it, right? So the idea is simply this. Well, yes, I have line L and any point. Put the point anywhere you want to. Anywhere you want. There's an infinite number of ways, right? I can draw that line going through that point any way I want to. There's an infinite number of lines. But this postulate is guaranteeing that at least one of those lines is going to be parallel to the line that I drew. And that's it. That's all it's simply saying, the parallel line postulate. All right, guys, thanks so much for joining me for this set of videos. Hopefully at this point what you've seen is that we can take our postulates and theorems, and by writing a converse statement, by switching the hypothesis and the conclusion, we now have a way of proving that lines are parallel. We just did a number of example problems together. Hopefully you'll get an opportunity in the homework and things like that to practice a little bit more. And of course, as we continue to work our way through this chapter, you're going to see these ideas over and over again. I really had a good time working on this with you guys. I'll see you next time.